Welcome to the Explainer. Today, we're jumping straight into one of the absolute most frustrating, head-scratching bugs you can ever encounter in programming. Specifically, we're talking about text parsing and indexing in Haskell. We're going to unpack a super elegant algorithmic solution to squash a very specific, very annoying kind of string collision error. If you've ever dealt with recursive loops or text formatting algorithms, untangling this is going to be incredibly satisfying. Okay, let's dive right in.
I want you to think back for a second. Have you ever written what you thought was a perfectly logical search and replace script? You hit run, and instead of beautifully formatted text, you get absolute garbage, right? A regex goes completely rogue, or a recursive loop disastrously overwrites itself just because it got confused by its own previous modifications. It is such a common developer pain point, and it's exactly the trap we're navigating out of today.
So, to set the stage here, we're looking at a real-world project documented by a developer named Ang. The project is called Access to eBook, and the goal is highly specific but incredibly useful, taking standard TXT files and converting them into fully indexed, nicely formatted PDF documents. Now, to make the jump from plain text to a beautiful PDF, Ang is using Typst, which is a really powerful markup-based typesetting system. But to actually leverage the indexing and bookmarking features of the final PDF, the Haskell code needs to scan the text and wrap specific keywords in Typst markup tags. Sounds pretty simple, right? Just find the words and wrap them. Well, as you'll see, it's not quite that easy.
Listen to how Ang describes it. Quote, "This is probably one of the most intriguing problem I've encountered so far within working on this project." End quote. When a seasoned developer calls a text replacement issue their most intriguing problem, you know for sure we aren't just dealing with a simple typo. We are dealing with a fundamental, tricky logical puzzle regarding exactly how machines read and process sequences of characters.
The root of this whole puzzle actually has a formal name. It's called ambiguous overlapping substitution, or a bit more simply, a collision error. So the crucial point here is this. When you have a list of keywords you want to find and replace, and some of those keywords share the exact same sequence of characters, meaning they overlap, your program's logic basically starts to trip over its own shoelaces. The act of replacing one string instantly corrupts the text, which makes it literally impossible to correctly replace the next one.
All right, let's make this abstract concept a bit more concrete. Meet our main characters for today's micro case study, the keywords foo and foobar. Our target sentence that our Haskell script needs to process is simply, "I love foobar too." We need the program to find our keywords and wrap them in Typst markup. But here's the catch. Foo is literally sitting right there inside of foobar. If we just run a naive replacement loop, the order in which we process these two words dictates exactly how our code is going to spectacularly fail.
This brilliantly illustrates the nightmare scenario. If we process the shortest match first, we get an absolute failure. The output becomes, "I love hashtag index bracket foo, close bracket bar 2. If we flip it around and go longest first, it's arguably even worse. We end up with nested broken markup where foo is tagged right inside of foobar. Both of these are completely invalid Typst code and will break the PDF generation entirely. No way around it.
So why does this fail so badly? Let's step into the shoes of a senior developer debugging this. If we go shortest first, the script finds foo inside the word foobar and replaces it with markup. Now the actual word foobar no longer exists in the text. It's been totally fractured into a tag and the letters BAR. So the second keyword is never even found. Okay, what if we flip it and go longest first? Well, we successfully replace foobar with its proper Typst tag. But then, on the secondary pass, the script scans the new text, looks for the word foo, finds it sitting inside the actual Typst markup we just generated, and replaces it again. It actively corrupts the syntax of its own output.
So how on earth do we get out of this trap? We desperately need a way to process the text without our subsequent passes accidentally reading the output of our previous passes. The incredibly elegant algorithmic solution Ang recommends here is the two-pass-sentinel approach, better known in the community as the hide-and-swap technique. It's a beautifully simple concept once you see it in action.
Let's break down this hide-and-swap solution into a really clean, logical three-step procedure. Step 1, we sort keywords by length, descending. Step 2, we replace the keyword with a unique sentinel. And finally, Step 3, we replace that sentinel with our actual Typst markup. Let's look at each of these steps closely to see exactly why they are the magic bullet for our collision bug.
Step 1 is sorting by length descending. This ensures foobar is always processed before foo. In the Haskell code, Ang uses a sorting function to guarantee this exact order. This is absolutely crucial because it immediately eliminates the shortest first failure we saw earlier. By prioritizing the longest strings, we guarantee that we are capturing the largest possible target words before we start chopping up smaller substrings. But, as we know, longest first alone causes that nested markup corruption. And that is exactly where step 2 comes in.
Enter the sentinel. It's a massive, weird-looking string, specifically \NUL K0 \NUL. Think of a sentinel almost like putting a keyword into the witness protection program. A sentinel is just a placeholder string that is guaranteed to never naturally appear in your real text. In this case, wrapping a placeholder like K0 in null characters does the trick perfectly, because foo or foobar are now completely hidden behind this untypable, invisible mask. The string matcher will just completely ignore them on all subsequent passes.
Let's see this actually play out in real time. In the first pass, the script finds foobar and immediately swaps it for our sentinel placeholder. The sentence is now, I love sentinel too. Now, when the script does its next check for the smaller word foo, it scans the sentence, finds absolutely nothing that matches foo, and just safely moves on. Once all the keywords are safely hidden behind these sentinels, we execute the second pass. We scan the document one last time, find our sentinels, and swap them out for the complex Typst markup.
So, to wrap our heads around why hide and swap is such a total game changer for overlap bugs, first off, shorter keywords like foo are just no longer visible to the matcher if they were part of a larger, already processed word. Second, and honestly most importantly, it entirely prevents the secondary pass from corrupting existing Typst tags. Why? Because the complex syntax containing the word foo isn't even generated until the very end of the process. It safely isolates that complex markup logic completely away from the vulnerable search and replace logic.
It's honestly a fantastic reminder that sometimes the absolute best way to solve a collision in your logic isn't to just write a more complex, regular expression, but simply to hide the data until it's safely ready to be processed. So, I'll leave you with this thought-provoking question to chew on for your own projects. Where else in your code are invisible sentinels waiting to solve your overlap bugs? Whether you're writing in Haskell, Python, or JavaScript, this architecture pattern is an absolute lifesaver. Thanks so much for joining me on this explainer. Keep your logic clean out there, and I'll catch you on the next one.